All right, I think we are ready to go. Well, good afternoon, everybody. It's great to see you guys. Today we have Jesse Havens with us. He is from Fracture ID, and I was chatting with a few of his colleagues a couple months ago, and I'm always a sucker for any type of tool that could help identify fractures or anything like that in the subsurface. So was really happy whenever they said they would be willing to give us a webinar today. Um, so Jesse, he has studied geophysics at the Colorado School of Mines and received his bachelor and master's degree before leaving his PhD early to work at Fracture ID, a great company. He specialized in experimental rock physics and contributed to projects ranging from artificial maturation of oil shale to calibration of 4D seismic studies. Early on at Fracture ID, he helped develop the numerical models used to transform the accelerometer measurements into geomechanical properties and built out the initial use cases. And he is currently in charge of the technology development and technical operations. Well, Jesse, thank you for being with us here today. I will let you take it over.
Let's share my screen here. Looks like it's up.
Perfect.
All right, thank you everyone for coming to my talk. We're going to talk about completions optimization using Drillbit geomechanics. And I think it's the Drillbit geomechanics is still relatively new for a lot of people in the industry. So I think we're going to go a little bit deeper into it than maybe Fracture ID or has really shared in the past publicly. So I'll give you a nice introduction all the way through the process till we get to the Drillbit geomechanics. Then we'll go through a couple case studies on completions optimization. But I wanted to cover the motivation first. So here I have a couple charts. Here on the left, we have starting in 1965 through 2022, various types of oil production that has, for some of these, already seen peak oil production. Now, this is almost all conventionals in specific countries that have seen peak oil production. But then right at the end, you start to see the US tight oil at the very top come in kind of the light brown. And then here on the right, of course, we have some great charts being made these days by Novi Labs. And this one is the unconventional oil production from the Permian. If you separate out the beginning of production by year. So we see, over time, we're seeing this increase in production in the Permian, but the fall off is quite aggressive. Now, the other thing to keep in mind in unconventionals, we're only extracting somewhere around 10% of the oil in place. So there's a lot left to be desired on what we're producing. We need to continue drilling, continue producing from unconventionals, which means we need to find new ways to optimize the way we're producing. Part of it, or a large part of it, I think, is on the drilling side. And then there's also work to be done on the completion side. But so today I'm going to talk about the completion side, but these downhole high frequency measurements also have a lot of benefit for the drilling side. So an overview of what I'm going to discuss is I'm going to introduce the high frequency downhole measurements, just show the time series and how we tie it to the surface data. So everyone's just very clear about the measurements we're talking about here. And then I'll discuss a little bit how we transform these high frequency measurements into elastic properties. And then we'll get into the completions optimization case studies. And these are both case studies that are publicly available. There's papers published on both of these. So you can go and do more research on exactly what happened. basically we have a Powder River Basin completions study that used limited entry and then adjustments to their treatment size based on the downhole measurements. And then we have a Permian Basin project that was more of a science well. So the exact optimization strategy is still somewhat up in the air on that one, but there's some interesting correlations and some good information on what's happening in the Permian based on both the downhole geomechanics and then some other support diagnostics. All right, so let's start with the downhole measurements. So what are we talking about here? So Fracture ID started back in 2015. We got our first actual in-house data set in 2016. And at the time, there was only one available vendor. Now, virtually any bit that you're drilling with, you can instrument it with some of these downhole sensors. So the actual sensors that we're talking about are 3-component accelerometers and gyros. And so you can either essentially have a dart that is that we call center line, so it's centralized in the center of the drill bit, or you can have what we call collar mount, these pucks that have that have some radius away from the center of the bit, but they have all the same types of measurements. So multiple vendors, multiple options on how you can instrument these things, but they're all high frequency, 800 hertz and above, and they're actually in the drill bit. So there's no type of operational problems that occur. You just have your vendor instrument the drill bit with these measurements. Now, of course, with all of these, we're talking about fairly dumb sensors. We're not talking about some sort of advanced multi-component geophone, for example. So with both of these, what Fracture ID is actually after is the vibration modes. So you're going to have some sort of axial load, some sort of centripetal load. That's more of an industry term, because again, these are dumb sensors. And then you'll have some sort of torsional load. So whether you're in the center line or the collar mount, you will be able to extract all of the different vibration modes. How they present themselves on the various sensors will be slightly different. But those are the two main types of placements that you would encounter in the field. And so once you grab the actual data off of these tools, it's going to simply look like that time domain signal that I'm showing in the upper left. So it's just going to look like a bunch of jitter going on. So without doing anything else, there's quite a bit you can already do with the data. One thing, you can apply a fast Fourier transform and take the time domain data into the frequency domain. So that's what I'm showing in the bottom left. So we take small time samples, apply an FFT, and then we have some type of frequency amplitude at each frequency. And then you can also do some physics modeling, because you have, for example, in a horizontal well, you have this accelerometer that's rotating, and you have a fixed vector signal in gravity that should have some sort of acceleration response. You can actually model two of the components of the accelerometer and combine that information with the gyro to do, right off the bat, a little bit of QC to ensure all of the measurements that you're getting are making physical sense. So if you do these calculations right and you're getting clean measurements, you should be able to compute a gravity wave signature that shows up at 1G. But of course, that's not super interesting, not tying any of the measurements to your actual downhole environment. So the next step is to actually take those high frequency measurements and tie them to your surface EDR measurements. So here's an example where if you look about midway through this track, you start to see the high frequency measurements. So the SSCM axial min, axial RMS, axial max, everything to the right is the high frequency measurements. Everything to the left is what you get from your surface EDR measurements. So we have a time in the first track. We have a depth from your bit depth, so you can tag where in depth you are. And then we have things like the rig state. So you can see in here you have rotary drilling in kind of that red color. And then you have in the slips in the blue. So if you look at the time periods that you're in the slips, you should expect to see no acceleration. Now here, of course, we've already tied the downhole data to these surface EDR measurements, but this is basically the process that you would use. You look for all of the flat acceleration time periods, and you tie it to times when you're not actually progressing in depth. And then on the far right, if you look, there's the fast Fourier transforms. So you can see that just looking at the spectra of the tied time samples to your EDR, you're starting to see some pretty dramatic changes in the acceleration response downhole. And so, with a completely different talk, we could talk about some of the drilling applications. Here we're focused on the geomechanics, but there's a lot of optimization you can do around, equipment choices, downhole practices, drilling practices, once you have this high frequency data in hand. And so if we kind of tie this all together for the next step of the geomechanics, we have the time series data here in the middle. You see that very jittery blue response. In the upper right is the full well surface EDR measurements. There's a little black arrow that says where we are in section at this particular snapshot. In the upper left, you have what the surface measurements are doing over this time period, which is about 10 seconds of drilling. So you don't need to squint. There's no movement happening in the surface measurements. So there's a lot more information in the downhole high frequency data for sure than what you can get from your surface measurements. But then down in the lower left, we again have our windowed FFTs, where we can look throughout this signal what's happening in the frequency domain. Then beside that, we have a plot of the displacement amplitude with frequency. So once we're at this stage where we know we're actually drilling, and we can form these depth bins, pull out chunks of time, then we can start to pull out spectral attributes. And so as we go into the geomechanics evaluation, the spectral attributes are what we're going to actually be using the process for geomechanics. But then here on the right, we can actually take these windowed spectra and we can stack them into a specific depth. So say you want a depth spectra every half foot, you can stack all of these windowed FFTs into a half foot bin. And so what we're showing on the right here is what we call depth spectra, where we've done that for this entire well or this entire run. And so on the y-axis, you have depth, and then you can see the frequency on the x-axis, and then the highlighted amplitudes with the color scheme. So we can take the depth spectra, we can start applying those spectral attribute models that I was just showing. But many times before we want to take that next step, we will filter data first. And so here is an example of a very noisy data set. This is still, the datum is still in time, so we haven't stacked from the depth yet, but we're looking at these windowed FFTs as we progress through time. And what you'll notice in this case, if you look all the way on the left, that's the raw input data. And you see a lot of vertical high amplitude streaks. And then probably the other thing you might notice is there's a bit of a fanning response that you can pick out. So that's a well-known, everything pretty much that you can see here with your eyes is some form of resonance of the BHA. So it's either some equipment is being excited at its resonance frequency, or there's some changes in the pipe diameter that are causing resonance. But basically what we're going to do with this raw input data is we're going to apply this family of filters that try and predict based on past data what is about to happen in the future. So in general, it's difficult to predict the future. The only way we're able to do it here is if there's a repeated response from the BHA. So we don't expect drill bit as it's drilling through the rock and vibrating against the rock to show any type of predictive future response. We expect all those type of responses that we can predict well into the future to be related to the BHA. So that middle track is the forward prediction we've made using this family of filters. So you can see just how much that forward prediction looks like the input data here. It's because this is a fairly noisy data set. There's a lot of resonance. So we take that forward prediction, we subtract it from the input data, and we end up with the plot on the right, the residual. And this residual, now you can see that there seems to be some consistent changes in the amplitude across all frequencies. And so we recognized over time this broadband changing the amplitude response across all frequencies is the geomechanical response as you're drilling. So in just an example, once we apply that method throughout the time series, and then we do our stacking into the depth spectra, here's a relatively severe example where the top is the raw spectra, very noisy, and the bottom is that filtered response. So a lot more broadband features, a lot more correlation between the different channels. This is what we would actually process for the geomechanics. And so just finishing out how we get to our raw geomechanics responses from the accelerations. We've designed our inversion techniques so that they are not too sensitive to the bandwidths that we actually use. So we have these filtering techniques, we've stacked the data, into these depth spectra, which has suppressed some sources of noise, but still, if there's something in the signal that we think we need to avoid that is not related to the geomechanics, we can just move our bandwidth selection around that source of noise. So once we've selected the bandwidths, then we can make our spectral estimates. These come from seismology. They happen in the frequency domain. And with them, we can estimate the stress and strain of the rock. Once we have that stress and strain, we've gone through a lot of testing to figure out where exactly to place that in an elastic model. And so we can take that stress and strain, plug it into Hooke's law, and solve for a variety of elastic models. So we'll solve for an isotropic, a VTI, and an HTI model. So if you go into actual rock properties now, relate this to some geology, when you're looking at a VTI anisotropy, typically what you're looking at is the background intrinsic anisotropy of the rock. So microscopic layering is basically what we're looking at here. Most US basins, you'll see within a specific formation, a strong correlation to the amount of clay content as the VTI anisotropy goes up. But it can also be due to just fine layering of the medium. But it has to be on the micro scale, very small scale. And then we can also run it through HTI anisotropy. We don't have specific examples we're talking about here where we try and use the HTI anisotropy. But we go ahead and interpret the HTI anisotropy as fractures. So areas where you have, large plumes of HTI anisotropy, we've gone through and basically plug those in as fracture attributes. And so we can provide some sort of indication along your lateral where you have larger fracture swarms. So if we return, back to that example of the adaptive filter that I was showing, here on the right, we now have the fracture ID indicated VTI properties against dipole properties. So in blue, in both cases, you're seeing what the dipole sonic measurement of the property. And then black on the top is the unfiltered spectra translated to geomechanics. And then on the bottom, you have the filtered spectra translated to geomechanics. And so for a VTI medium, if you want to calculate the elastic Young's moduli and Poisson's ratios, you can actually produce 2 Young's moduli and 3 Poisson's ratios. Here we're showing 2 Young's, 2 Poisson's, and then on the right we have Thompson's gamma parameter, which is a unitless anisotropy parameter. So before we filter out BHA resonance, it's hard to actually capture the geomechanical response. Once we filter all that out, we apply our again spectral attribute estimates, calculate stress strain, run it through Hooke's law. Now we have a pretty good match here to what's happening with the geomechanics along that lateral. And we can look over time at the very beginning of the company. Some of the hardware solutions were a little challenged. So back in 2016, when we first started doing commercial work, again, there was only one vendor, and using our most up-to-date processing techniques prior to 2020, this is the match we could get all the way here on the left. So again, 2 Young's, 3 Poisson's ratios, and 1 unitless anisotropy parameter that we're showing, Thompson's gamma. So, even with our latest processing, there were some challenges with the tools. In 2017, we had the next kind of wave of innovation on the hardware side, and then by the time we get to 2018, we're snapping with the geomechanical properties pretty closely. And so now we're in 2024, and all of the hardware vendors have continued to improve their responses. over time, we expect this to, basically be giving very consistent properties with what you get from the dipole sonic. Okay, so going past the base geomechanical properties that we can provide, we also can estimate depletion. So how we estimate depletion is we use the gamma ray and the BTI anisotropy to predict what the Young's modulus should be doing. And so the inherent assumption there is that gamma ray will not change with depletion, and also that the BTI anisotropy will not change with depletion. That unitless term for the BTI anisotropy, we have, if you consider that it's mainly related to clay, so microscale layering to the stress field, or it's fine layering of properties. We don't believe either of those things can change rapidly just because the rock has lower pore pressure inside of it. So that's why we use those two things. And so we take that estimated Young's modulus value and we compare it to our measured Young's modulus value. Part of this started out with just field operations, but if you dig into the rock mechanics literature, once you go beyond the effective stress that a rock has seen, you start to see a rapid change in the mechanical properties of the rock. So we think many times what we're seeing is we've gone beyond the effective stress the rock is seeing, and you start to see pore collapse or compaction mechanisms start to take hold. So you can see quite a bit of an increase in the Young's modulus when that occurs. So I'm going to start talking about one of the case studies now, starting from our estimate of the depletion. So this is the Powder River Basin. This is higher permeability than most U.S. unconventionals. So it's almost like a quasi-conventional case study. But basically here, what I'm showing is we have the gamma ray, we have the depth in the lateral, and then we have the YM trend in black. So this is what we expected the Young's modulus to be doing based on vertical offset pilots. And so we used, again, gamma ray and BTI and anisotropy to figure out what this curve should look like. The red curve is what the Young's modulus actually did. And so you can see at the beginning of the well, there's a large delta between the black curve and the red curve. And then as you get into the middle of the well towards the end, there's quite a bit more agreement. They're almost aligning with each other. So we use that delta, and we do actually calculate an exact pore pressure value. So the next track, you can see the static pore pressure that we just got from the client. So this is just going to be based on the pore pressure gradient and the TVD at that particular time, that particular depth. And then the red is the variable pore pressure that we computed based on the deltas. And so we just subtract those two, and on the right, we have our depletion curve. So there's different levels of calibration that you could do for the actual pore pressure value, but at the least it indicates what portions of the lateral to us look like are pore pressure depleted. So if we look at a map view of this well versus offset wells, we had a lateral producer that covered about half of this lateral. And so that chunk where we saw these huge pore pressure depletion values. It was right over, it was right across from this producing well, and in particular where the well was closest, we saw higher pore pressure depletion values. And so from an optimization standpoint, the first thing that we usually always recommend for people to do is a limited entry optimization. So the minimum horizontal stress is the primary geomechanical curve input. And the idea here is you want sufficient perforation friction to open all the perfs within a stage. And the perf friction is a function of the shots, the hole size, and the flow rate. So it's similar to if you have, an old-fashioned sprinkler with a bunch of holes spraying the water out. So if you start to cover up some of the holes, you expect a further jet stream. And so if you could imagine changing the hole size, you would expect the jet stream to go down. So in this case, the way they had their original strategy, they had 100% perforation efficiency. And I'd say over the last 5 years, I've picked up on limited entry strategies. So they tend to be on the more aggressive side. So they are almost certainly getting 100% perf efficiency or something close to it. So in this case, the optimization is to make some of the stages larger, not change the amount of entry points, but make some of the stages larger so that it's faster to pump and you can save money in the operations. And so you can see that table on the left, basically what we did with the geometric versus the geo-informed completions. We were able to reduce the stages by 8, and they still got 100% perforation efficiency. And how they validate this is they usually pick a few stages to do step down tests. So this is basically normal operations for them now. They use us to decide, how large or small each of their stages are, without changing anything specific about the perf strategy. They don't change the hole size or the flow rate or anything of that nature. So they were able to basically recover part of the cost of using the surface immediately by pumping less stages, having a faster completions job. But they did more than that. So they took the depletion curve that we generated and they had us do some modeling. So some Frac reservoir modeling. And they had different scenarios. So if you look in the bottom right, there was the orange scenario. That was the base design. So just geometric completions, everything as they usually do. And then there was a maybe more aggressive strategy in green, increasing the cluster count per stage. And I think adjusting the treatment sizes based on the depletion. And then the third one was what they actually went with. So that was basically keeping all of the materials for the well the same. So taking some of the materials that they were planning to pump in the depleted intervals and redistributing that material throughout the well. And so if you have already bought all the materials for the well and you don't have a lot of options for changes in optimization, you might want to go with that sort of strategy. But you look at the fracture flowing area estimated from the modeling, and there is actually very minor difference between the base design and the actual treatment size. But you go back over to the left, they had, in this case, a series of child wells that they had already drilled and completed some offset parent wells. And so they found a bunch of these child wells that they thought were comparable to the situation that they were in with this set. And by doing this optimization, they actually saw more like a 30% uplift in production. So we think it probably has more to do with fracture-driven interactions. You're not going to be able to model exactly everything that's going to occur between a child and parent, without considering fracture-driven interactions and effects that you could have on the parent. So in this case, for both the gas and the oil, though, they saw approximately 30% uplift, and this has become their standard operations. And over time, they have seen a slight increase in their production overall, with the service being the only thing they change. Whereas basically across the field, operators are seeing a reduction in their production. So as their infill drilling next to parent wells, they've been able to not only maintain production, but they're seeing a slight bump while decreasing their operational costs. Now, I would say that that last example might be the easy example because it is, again, quasi-conventional. And if you compare Powder River Basin to the Permian Basin, where most people are doing most of their drilling, it's a lot less complex as far as parent-child interactions. How many vertical producers versus horizontal producers are in the area, and then the amount of wells that are being drilled next to each other. So this is an example from the Permian. This was a science well. It had quite a bit of support information, but they were not specifically doing the project just to optimize the completions around our depletion measurements. So what their objective was they were testing a bunch of different perf strategies across the lateral, and they were confirming the production performance with some supporting information. So not a concrete solution that I'm about to show you here, but a lot of good supporting information around this depletion analysis. So in the map view at the top, we have the well with gamma ray in the gray shading, and then the depletion curve in the green blue colored shading. You can see there are offset laterals that have been online producing for about 3 years. They cover about half the lateral, and then the stars are a bunch of vertical producers that have presumably been producing quite a bit longer. So you can see just based on this analysis, how much of the depletion profile is following some of these verticals, but you do see broadly more depletion as you cover these lateral wells on half of the well. So they use DAS DTS flow allocation. Certainly no expert in how this works, but in each of these cases, I'm trying to point out the heel side and the toe side. Actually, if we go back here, you have the heel on the right and the toe on the left. So the green field here is on the left, and it's close to the toe. And then the heel is on the right, and this is where you have offset depletion. So if you keep that in mind, look at this DAS DTS flow allocator. The green field here is on the right. So you can see there's not a lot of production happening in the green field area, but it's also near the toe. And so for us doing these depletion analyses in different basins, all over the United States and up in Canada, we've seen this trend quite often, that there is a maybe much larger heel bias to the production than people might have realized when they drilled the wells. So here we're seeing that heel bias, so they're actually getting fairly high production coming from the brownfield area. And then there are some spikes of production that you see in the middle here on 14,000, around 17,000 feet. So if we line that up with the depletion analysis, you can see that areas that are seeing these pockets of higher production are actually areas that we were picking out as depleted. And if you recall from the earlier slide, these had vertical producers nearby. And if you look at the gas production, there is also an uptick in gas around these areas. So kind of our working interpretation here is there is a huge downward bias in production. Pretty much across the board, we've seen that. There is a production increase due to the increase in gas in more depleted areas because the Permian can drop below the bubble point. So you see that uptick in gas. And then because of the strong heelward bias or toeward bias, however you want to look at it, there's actually a large portion of this well that probably got understimulated, is going to be difficult to produce any resource from. So in this particular case, we don't have any answers at this point. You will remember on top of this, they were trying to optimize their stage limited entry strategy. So there are some changes in here due to that as well. You can look at the paper if you want to try and figure out everything that's going on here. But we definitely think the Permian is going to be a unique completions optimization problem. But because of the bubble point being passed and just how many vertical and horizontal producers we have in the area. So we think that geomechanics will certainly be part of the solution, and the depletion will be helpful in just deciding how you do this. But at this point, we're just starting to work with people to figure out what to do with the mess that is the Permian. So that's essentially what I've prepared for you today. So I'll return to the overview. We went over the high frequency downhole measurements, the time series tied to the surface data, transformation into the elastic properties, showed some raw geomechanics comparisons with dipoles. And then we went over a couple of examples. One that I'd say is in operations mode in the Powder River Basin. And then in the Permian Basin, of course, we saw a more complicated response, but it's in progress. How we're going to go about helping people complete their wells in the Permian. And with that, I will just take any questions.
All right, thank you, Jesse. If anyone has any questions, please submit them to the Q&A box, and then we can read them out to Jesse, and he can field them one at a time. The first one that was submitted is from Nisikul Islam. How does the determination of mechanical rock properties differ with use of different BHAs? Does it make it harder or easier? For example, having 3 roller reamers and 4 roller reamers will have multiple harmonics and resonance frequencies.
Yeah, there are certainly some BHAs that are more difficult to process than others. We don't really come across any that we absolutely can't process. But if you have a conventional BHA, the signal tends to be cleaner than if you have rotary steerable. With the rotary steerable, we can fit more measurements down there, so we have multiple shots at getting a good signal. So yeah, there's absolutely differences in the quality of the measurements, and it mostly has to do with resonance.
Okay, great. The next one comes from Colin Sayers. You mentioned estimating stress and strain from the filtered spectra, but didn't explain the step. Could you explain the step?
Yeah, so we're using modified Eaton's equation. So an assumption of what the BO's coefficient is, and then instantaneous stress calculated from the elastic properties. So you could try and do a more comprehensive, more complex model and just use the elastic properties as your input to solve for the other parameters. But it's yeah, we've mainly just been using the instantaneous stress and the elastic properties.
Nader Fardin asks, many thanks for a great and informative presentation. I've not seen any calibration for rock mechanical properties as well as minimum horizontal stress versus lab test data. Could you please elaborate more? What is the maximum depletion in pressure in unconventional reservoir?
Maximum depletion and pressure. So the types of laboratory measurements that usually cover this branch of rock mechanics are usually pore compressibility measurements. So the reservoir engineers are interested in pore volume compressibility. But it's just a translation of terms on some level. And then you have elastic properties that you can measure while you're doing these pore volume compressibility measurements. And we would relate our measurements to elastic properties most closely. So that's what you would be doing there. As far as calibrating the actual pore pressure depletion values, there have been downhole cemented in pressure gauges that we've looked at, but then you're basically down to defits. You have to try and have a defit in a virgin rock lateral at the toe, and then you have to have it in a depleted lateral. You can of course look at frac gradients and whatnot. Yeah, so there's multiple ways to improve the calibration of the pore pressure estimates. In the absence of any of those, we have a relative measure indicating where along the lateral you see pore pressure depletion.
Okay, Umesh Prasad asks, did you use 2 Young's modulus and 3 Poisson's ratio in your application analysis? I did not see it.
In the actual application, so we for sure use the VTI anisotropy. So we use the unitless Thompson parameters to estimate what we think the Young's modulus should be doing. We might not have gone through the full calibration for the minimum horizontal stress estimate. So it depends on the formation, whether we think it's absolutely critical to go through that calibration, or if we just use the isotropic response. So Powder River, it's a sandstone. I doubt we would have gone through the full calibration. We might have done it in the Permian. But things like the Marcellus, Utica, we'll definitely go through full calibration every time.
Okay, another question from Umesh. You explained very well HTI and VTI. Does it happen that we have both? That means orthotropic. How will you handle if such is the case?
Yeah, I mean, we definitely do have both. We solve for both. So really the issue there is we're in an underdetermined system. And so we have to change the framework of the inversion model to try and isolate the signal that we're trying to solve for. And so if you're in an overdetermined system, in the seismic domain, many times people do a similar thing, but they have far more than enough unique measurements. It's just trying to find a stable solution. Here, it can be more problematic if you're in a highly VTI system to get a good HTI answer. Yeah, that's certainly an issue. It's mainly an issue with the HTI solution.
Okay, question from Julian Yao. Do collar-mounted and centerline sensors acquired data require different processing?
Yeah, they partially require different processing. Yeah, you have to isolate the correct vibration mode that you're using for a specific stress and strain. But it isn't wildly different. We at the beginning we thought it might be, but turns out you can get a pretty clean representation of all the vibration modes from both of the types of sensors.
Okay, this is from an anonymous attendee. Have you used over-the-shelf software like MATLAB to perform forward modeling, or is this a proprietary method?
Perform forward modeling. Well, I mean, we're not using MATLAB. We're Python, mostly with Rust and C. So we write our own software for the processing, but we use methods. The forward prediction methods are somewhat ubiquitous in various geophysical applications. It's just our specific application is maybe a little bit of a mix-up, a little bit different, but not too much different.
Okay. And then a question from Nick Brissett. How does MSE on rotary versus soft torque drilling vary across the string and on the bit within the BHA, and pucks and sliding compared to rotary drilling affect these frequencies?
So the sliding, there is a like convolutional method type of correction we make during sliding. So that certainly has an impact on the vibration response. And as we showed, we're looking for a broadband response. Random noise kind of looks like a broadband response. So anytime equipment goes on and off, completely on, completely off, that can cause a disturbance in our methods. Other than that, I mean, we're always looking for a breakdown of the elastic model, and so we will flag things if the elastic model breaks down. It won't necessarily be for a specific drilling event. But how does the first part of that question was how does the various sensor placements and whatnot affect the signal?
It says, how does MSE on rotary versus soft torque drilling vary across the string and on the bit within the BHA?
Yeah, I mean, I guess that's not something, any small change to the BHA we see in the acceleration data. So I don't know that we've done general studies on exactly how it changes. Our drilling SME would maybe have a better answer for that.
Okay, thanks. Any other questions from the crowd? If not, I'd like to thank Jesse for giving a wonderful talk on behalf of PSGD. We will be putting this recording out to our YouTube page, and stay tuned for further webinars. If anyone has recommendations for good webinars that they'd like to see or think the group would like to see, don't hesitate to send recommendations our way as well. Otherwise, thanks to everyone and have a great day. Jesse, thanks again from us.
Yeah, thank you, Jesse. Appreciate it.